Hello and welcome to this week 10 TA session on constraint and unconstrained optimization. So it's almost 3 p.m., around 3 minutes to 3 p.m. So I'll wait for a few more minutes and to see if anyone joins, and then I'll get started with today's content. All right, so it's 3 p.m. already, so I'll get started with teaching the week 10 assignment problems that you have, I think, already solved. And then I'll move on to discussing some of the similar topics that you'll find in the week 11 assignment. Okay, so the topic of discussion today is first is week 10 assignment solution. And then similar problems to week 11 assignment. All right, so these are the things that I'll be discussing, and in week 11, the topics that we'll find is nonlinear constraint optimization with multiple variables. So I'll probably discuss that as well. So let me get started with the week 10 assignment solution. So let me write down this first. Week 10 assignment solution. Okay. So let's solve this 10 problems one by one. Some of them might be very easy, like one line kind of an answer. But anyway, for the sake of completeness, let me go through this. Okay. So the first one, tells you minimization of min of fx subjected to g of x less than equals 0 and x greater than equals 0. So which of the following is true or is or are true for the above optimization problem? So which of the following is or are true? Right. So what you have is the options I'll write down. Option A is grad of f and grad of g are parallel to each other at the optimal point. The next option is they are perpendicular to each other at the optimal point. So, okay, we have one person joining. Okay. Uh, Hi, Samit. So I'll discussing the week 10 assignment solution first, and then probably I'll discuss briefly about the week 11 assignment. If you have any doubts, you can ask me also regarding this week 10 assignment. But yeah, I'll be going through all these problems and some of the problems that have some issues. I noticed that. Okay, so the option B is this grad of f and grad of g are perpendicular to each other at the optimal point. Option C is they are oblique to each other or to each other at the optimal point. And finally, what you have is none of this. So it's a single constraint problem. So in this case, what you have is the directions of, so this is the direction of your grad of f, and this will be, suppose this is your optimal point. This should be your direction of grad of g. So they should be opposite to each other, and if they are opposite to each other, that means they are also parallel to each other. So option A will be the correct answer here. Yeah. So answer is A. So let me move on to the second problem. So not much to discuss in this first one because anyway this has been discussed in the class, I think. Second one is min of fx subjected to g. This is gi of x less than equals to 0. I think that's written. And x greater than equals to 0. So here it is mentioned that if gj of x is an active constraint, then for the feasible direction s, which of the following is or are true? Actually, this should not be gi of x. I think there is some typo here. This should be g of x. So this is kind of a bunch of constraints, kind of vector you can assume. But the single constraint is represented as gj of x. Anyway, but that's not the major thing in this problem. So the options are S transpose times this dot product of these two equals 0. This is another one greater than equals to 0, or is it less than equals 0, or D is none of this. So in this case also, I think this has been discussed in the class as well. So for the feasible direction and when you're taking an active constraint, then if you do this dot product, so this should be less than equals to 0. So this is for feasible direction S. And whenever we are trying to find out the descent or ascent direction, then we have to do this dot product in terms of the gradient of the objective function. Okay, so this is for feasible direction S. So the correct answer is this one. So option C is the correct one here. Okay, so the third problem is for the objective function fx, which of the following is not true? Okay, option A is if S transpose grad of f less than 0, then S is a descent direction. Okay, next is if S transpose grad of f is less than 0, then S is an ascent direction. So here we have the comparison in terms of the objective function value. So you can also verify it using some Taylor series expansion as well for this problem. Then S is a descent direction. And option D is none of this. Okay, so we check. Okay, so for this problem, what you can do is this is for descent direction. So suppose I give you this. So this will imply that this is a descent direction, which is typically performed in the minimization problem. And for the maximization problem, when you have this, then S is an ascent direction. So out of this two, which one? I think option A is correct, and the others are not correct. So option A is the correct answer here. So this is also fine. Now let me move on to the fourth problem. The fourth problem tells you minimization of fx y equals x minus 2y subjected to x squared plus 4y squared minus 2 less than equals 0 and xy greater than equals 0. Based on the above optimization problem, which of the following is or true? So yeah, which of the following is or true? So this problem has some issues actually. So it says at y equals 2 by 3. Okay, I'll just write it down like this. S equals 0, 1 is descent. B is S equals 0 minus 0.5 is descent. C is S 0 minus 1 T is descent. G is S equals 0 0.5 T is descent. Okay. In this case, first let me check one thing. The constraint is square plus 4y square minus 2 less than 0. But let's put xy equals root 5 by 3 root 1 by 3. So this gives me root 5 by 3 whole square plus 4 times root 1 by 3 whole square minus 2. So this is 5 by 3 plus 4 times 1 by 3 minus 2. So that's 3 minus 2, which is 1, but this is greater than 0. So that means this is not a feasible point. So there is issue. So not a point in the feasible region. Now, generally in this kind of methods, this steepest descent method or any this gradient descent method, you don't start or end up anywhere point which is not feasible. So it's anyway doesn't even make sense to find the direction in a point which is not feasible. But anyway, let me do that because since this is the problem anyway that is given. So for this one, to find the descent direction, I have to take the gradient of the objective function, right? So for that, what I have is f xy is x minus 2y, and this gives me grad of fxy, which is 1 and minus 2. So let me find out this one by one. So for the first one, S1 transpose grad of fxy. So it's 0, 1, 1 minus 2. So this is minus 2. This is less than 0. Next one is this one, which is 0 and minus 0.5. 1 minus 2. So this becomes plus, sorry, this one, which is greater than 0. For the third one, what you have is so this is 0 minus 1. This is 1 minus 2. This becomes 2. This is again greater than 0. And finally, there's the fourth one. So this is 0. This is 0 0.5. This is 1 minus 2. So this is minus 1. So this is less than 0. So the ones with the less than 0 sign will be the descent direction, and that has been asked here. So this is so if you ignore the constraint, so this one and this one, so this is descent direction, and this is also descent direction. So option A and D will be the correct answers then. That's A and D. Okay, so now let me move to the fifth problem. The fifth problem tells me min of fxy. So it's the same problem, I think. But now they are asking about the feasible direction, right? Okay. And this is subjected to, okay, let me write down anyway. Yeah, so the idea would be to have this single, so this is a minimization problem with a single constraint. And the typically what happens is that the feasible direction and the descent direction could be of in the opposite to each other. That might happen as well. So this probably is the case here. Uh, so whichever is feasible might not be the descent direction because of anyway you're starting from a region which is not feasible at all. So there is this confusion in this problem. So there is this feasibility issue. So I don't know how why it was this point was given like this. It's because of that everything is kind of messed up in this problem. Anyway, let me still do this. So which of the following is true? So at xy, so it's the same problem, the same point, which is not in the feasible region. So the options are S equals 0, comma 1 is feasible. B is S equals 0, comma C is 0, comma minus 1 is feasible. D is okay. So this is absolutely fine. Now let me start with this. Okay, so here I have to get the gradient in terms of that constraint. So my gx here is x square plus 4y square minus 2, and grad of gx is nothing but 2x, and this will be 8y, and at that point, which is root 5 by 3, and this would be 8 times 1 by 3. So let's add, and this would be around 20 by 3. This would be uh, this I think could be root 64 by 3. Okay, let me just quickly double check. Okay, or I could have kept it as it is, it's not a problem. Right, so now uh, let me do the same kind of exercise here again, but with the, so this will be, I think I've written it wrong, so this should be g of xy, this should be grad of g of xy. So now what you have is S1 transpose grad of g of xy. So my S1 is 0, 1. This is so I will end up with this same thing. This is greater than 0. Next is S2. So that's 0 minus 0.5. So this becomes minus 4 by root 3. And this is less than 0. Next one is again 0 minus 1. Okay, so this becomes minus 8 by root 3. This is less than 0. And finally, it is 0 and 0.5. This should be this. So this will be 4 by root 3. This is greater than 0. Now, I think the first or the second problem had this kind of a issue is like if it is less than 0 and if it is an active constraint, then that's a feasible direction. But the thing is that this constraint is not active here. So it's not, I think, mentioned in the class as well, what happens when the constraint is not active. Mm, but the idea here is that, so that's the confusion here in this problem, is that, uh, okay, let me just check what was the answer that was provided. Just a minute. Yeah, A and D is the correct one. Okay, so the idea here is that, so let me write down, note that gxy less than equals 0 is not active. So it is violated actually. It's not active uh, at xy equals root 5 by 3 and 1 by 3. So in that case, what will happen is that you will pick the greater than 0 ones because it's the opposite condition of when it was active. So if it is not active, then you pick this one, and you have to pick this one. So this could be your feasible direction. And this is also could be your feasible direction, right? But the issue here is that you will still, I think, end up with another point which kind of violates your uh, so in that case also, if you take a step, positive step also, you will again end up in the infeasible region itself. So I think this comment is wrong. So what I feel here is that the question has an issue, and ideally this should have been the feasible direction, and this should be the feasible direction. So I think the answer could be in this problem should have been B and C, because then only you're reducing the value of y and you're moving towards the feasible region. So for in my understanding, it should be B and C, but I don't know why this question was having some issues, some faults, and also the answer that was provided was A and D. But anyway, you can raise this issue in the discussion forum later if you want, but probably the instructors will take care of it. Okay, so let me now move to the sixth problem. So let me just quickly check which ones have the issues. Okay, sixth problem is minimization of effects. So this is subjected to GIX less than equals 0 and x greater than equals 0. Which of the following is are true? So let me quickly write it down. Okay, so in this case, the options are option A, which is lambda I greater than equals 0 corresponding to. So that's your dual variable that you can also think of. This lambda I. Okay. So this is option C is either of them can be true. D is none of this. Sorry about that. In this case, the answer is option A because this corresponding dual variable has to be positive or non-negative. Okay, so option A is correct. So this lambda I is greater than equals 0. So that is fairly straightforward. Then let me move on to seventh problem. The seventh problem tells you this is related to the KKT conditions are sufficient for the existence of the optimum point. Okay. And which of the following is this the necessary KKT conditions are sufficient for the existence of the optimum point. Okay. So in this one, let me write down the options. Option A is fx, which is the objective function, is convex and constraints set gx is concave for a maximization problem. Next is fx and gx are convex for a maximization problem. Okay. Option C is fx and gx are convex for a minimization problem. This is a convex optimization problem. And D, fx is concave and Gx is convex for a maximization problem. So in this case, what you have to do, you have to do some sort of this should be a convex optimization problem, right? Answer is a convex optimization problem. So that means Gx must be convex regardless of the problem. Fx is convex for a minimization problem. Now, for a maximization problem, Fx is concave implies that minus of Fx is convex, and now you have a minimization problem. So by looking at this, you can tell that option C would be correct, and option D is also correct because you can convert it into a convex optimization problem. But the other options are not correct because either Gx is itself concave or the objective function becomes concave in the case of a minimization problem. So the answer is option C and D. So these are your answers. So that's fine. Now I have three more problems left here in this assignment. So let me solve that. Problem 8 is, okay, I'll write it down and just take a couple of minutes break and just okay. Now let me write down the eighth problem. Okay, so it is minimization of fx subjected to g I of x less than equals 0, and you have x greater than equals 0. So which of the following is or are true? Option A is either gix equals 0 or the corresponding multiplier, which is the Lagrange multiplier, corresponding other dual variable, you can think of it as well. Lambda I equals 0. B is If Gix is 0, then lambda is 0. Either of A or B can be true, and the final one is none of this. Okay. So in this case, this is basically the problem of complementary slackness condition. So the answer is complementary slackness condition, which is nothing but so your constraint is Gix less than equals 0. So that means lambda I times Gix. So this is equals 0. So it's either lambda equals 0 or Gix equals 0. And when Gix equals 0, then lambda I can be, so here it should be lambda I greater than equals 0. Right. So option B is not true, option C is not true, and option A is actually true. So any of the two has to happen, and D is not true. That means so option A is the correct answer here. Yeah, so this is A. Now let me move on to the ninth problem. So this problem have some issues, I think, as well. So while solving it, I don't know how they have got the answer, but I think that's not the correct answer. But anyway, let me check if I'm getting it or not. Okay, the ninth problem is minimization of fxy 7x squared plus 6x plus 5y squared subjected to x plus 2y less than equals 10, x minus 3y less than equals 9, and xy greater than equals 0. Okay, so say solve the above optimization problem. The options are f star f star equals 95. Next is f x star y star is 114.06. C is f star y star was 709.2, and option D is F is 1009. Okay, so the issue in this problem is you can notice if you put it as 0, 0 origin, then also the constraints are satisfied, and the objective function value that you get is 0, but all the objective function value given in the options are positive. So that means this problem has a flaw. So let me see if I can resolve it some way or the other. So I think the solution is given as 38 by 33 and 146 by 33. So just quickly I'll check it. It's 38 by 33. And 146 by 33. Okay, so if this has to be true, then in that case, let me check the constraints. X plus 2. Okay. Okay, so let me try with this. What I'll do one thing. So suppose instead of having it less than equals to, I'll try and have it as greater than equals to and see it like in that case whether we were able to solve it or not. So let me try that. So that means what we can do, we can convert it into less than equals type. Okay, and the rest remains as it is. And now I can start to see to solve it. So there is minor modification that you have to keep in mind for this problem. But let me now solve it. I'll write down this Lagrange function, which is a function of x, y, and lambda. So this is a minimization problem. So it's 7x squared plus 6x plus 5y squared. Then you have those multipliers coming in. So it's lambda 1 times. So what you can do, you can directly apply this. So it's x minus x minus 2y minus 10 and plus lambda 2 x minus 3y minus 9, and x and y are greater than equals to 0. I'm not writing that down. Okay, so now what you have, you can take this with respect to x, so that becomes 14x plus 6 minus lambda 1 plus lambda 2, and this with respect to y, this is 10y minus 2 lambda of 1 minus 3 lambda. So you can set these two zeros, so that might give you some expression in terms of x and y. Okay, or let me do one thing. Yeah, so what you can write from here is that lambda 1 minus lambda 2 minus 6 by 14. Y is 2 lambda 1 plus 3 lambda 2 by 10. Now you can write the complementary slackness conditions. In that case, what you will find is lambda 1 times this equals 0 and this one is equals 0. Okay, so from here it's lambda 1 equals 0, or uh, you have, okay, I think I made a mistake. There should be a minus 10 here. Okay, this is fine. And this should be plus 10 in that case. That's fine. Second equation is fine. On the first equation, so those numbers don't have any role to play. Yeah, so this means you have x plus 2y equals 10. And here you have lambda 2 equals 0, or x minus 3y plus 9. Now let me put the values of uh, x and y. What you can do, and multiply everything by 70. Okay, so it's 33 lambda 1 minus 37 lambda 2 equals 730. And from here you get, so that means it's 60. You can multiply everything by 70 again, I think. Okay, so that means it gives you, or is it correct? Let me check. Okay, looks to be correct, but okay, just a minute, I'll check and solve this. Okay, so what should be done here? Uh, there's one issue that I noticed is minus 37 lambda 1, 62 lambda 2 equals 660, but both lambda 1 and lambda 2 are greater than equals 0, so I don't know how this will happen. So, one way of probably doing it is okay. So, the good thing is that this cannot happen. So, that means in this case, what we have lambda 2 equals 0, that's confirmed. And that means it's 33 lambda 1 equals 730. And lambda 1 is 730 by 33, which gives you your x and y values. Your x is lambda 1 minus 6 by 14, and your y is uh, 2 lambda 1 by 10 or lambda 1 by 5, right? Yeah, so now if you calculate this, what you will get is you can multiply everything by 30. Okay, let me just quickly do it in my calculator. Yeah, it's indeed 38 by 33. And this one, it's 146 by 33. So this is your x star, this is your y star. So that means whatever is the problem. So the issue in that problem was that the first constraint should have been greater than equals to inside. So this is the correction. Okay. So that means your f star y star is 7 times 38 this plus 6 times plus 5 by. Okay, if you do that, let me do that on my calculator. Okay, it's indeed 114.06. So the option B is the correct answer, which was also given, but the question had a typo. Okay, now the final problem in this assignment, which also probably had a typo. This one is minimization of it. Screen froze for some reason. I'll figure it out. Okay. Don't know what happened to this app, but have to figure it out. So, close and open it. Okay, finally opened. Don't know what is the issue. Anyway, I'll just have one problem to solve and then probably we'll just have a brief discussion on the next assignment. But anyway, no one is here, so it's mostly be like closing to wrapping it up today. And the final problem is minimization of fxy equals x minus 1 whole square plus y minus 2 This is subjected to 4x plus 3y is 12 and x plus y. So this is the mistake. This should be less than equals to 4, I think. Because if it is less than equals 2, then I think the first constraint will not be satisfied in certain cases. Okay, so this is the problem. Solve the above optimization problem. Okay, so this is the correction. Uh, This could be, let me write down this. Okay, so the Lagrangian, so this would be minimization problem. So we can write Lxy lambda mu, since you have four things, right? Because one is equality type constraint. So let me write down it in terms of mu. 4x plus 3y minus 12 plus lambda. So del L del x, that gives you 2x minus 1 plus 4 mu plus lambda. Del L del y gives you 1 plus 3 mu plus lambda. And finally, have del L del mu, which is nothing but 4x plus 3y minus 12. So set all this to zeros. So we will have x equals 2 minus 4 mu minus lambda by 2. Okay, so this will not have a term in terms of uh, y, right? So what you can do, you can have a relation between lambda and mu. So lambda is minus 1 minus 3 mu. So that means it gives you x is minus, so that means plus 3 minus mu by 2. That's your x. And you can have it in terms of y as well. So it's y is 12 minus 4x by 3. 12 minus 6 plus 2 mu by 3. So it's 6 plus 2 mu by 3. So that's your x and y values. Finally, you have the complementary slackness condition. So that's lambda times 4, sorry, x plus y minus 4 equals 0. It's lambda equals 0 or x plus y plus 4. So in that case, what happens is that the x is so this becomes let me multiply it by 6. So that's 9 minus 3 mu plus 12 plus 4 mu is 24. That gives you mu equals 3. Mu equals 3 means lambda is minus 1 minus 3 mu. So this is not possible. So what you have is lambda is 0. That means this is 0. Mu is minus 1 by 3. So x becomes 3 minus mu by 2. So that's 10 by 3, 2. So that's 5 by 3. And y is 6 plus 2 mu by 3. 6 plus 2 mu by 3. So that's 16 by 9. So star is 5 by 3, 16 by 9. And what is asked in the problem? Okay, I didn't write down the options, I think. I'll just quickly write it down. Yeah, A is, so fx star, y star, A is 0, B is 3, C is 2.2, and D is 0.22. So now I have to find the check the function value. So it's 2 by 3 whole square, so that's 2 by 9 plus 16 by 9 minus 2, so I think that's 2 by 9, and that would be 0.22. So option D would be the correct answer here. Yeah, answer will be D. Okay, so that's all about the assignment and problems, and it had a few typos, and one of the options I think were wrong as well, so you can raise these issues if you want. Now I have some 40 minutes left in this session, so it will be discussion on similar problems. Assignment 11. Okay, let me just check if it is being recorded or not. No, I'll start that. Just Okay, so the first problem, let me discuss quickly everything. So, which of the following is or are true about Kelly's cutting plane method? So, it's on Kelly's cutting plane method, and the nonlinear objective function is linearized with Taylor series expansion. Constraints are linearized with Taylor series expansion. Both an A and B cannot be true. None of this. So, yeah. So, first one is directly from the lecture slides. So I'm not going to discuss this. Next is, I think, video 51 will probably find it. Next is uh, functions, and yeah, it's given. So obtain Kelly's cutting planes for the above problem at point. Okay, so let me solve a similar problem. So let's f equals x squared plus y squared plus 2x minus 3y plus 5. So g1 is suppose 2x squared plus y squared minus 8 less than equals 0, where g2 could be 3x plus 4y minus 12 less than 0, and you have in addition xy greater than equals 0. So you might be asked to obtain Kelly's cutting plane for the problem at x1 y1 will say 1. Okay, I modified the problem slightly. So in this case, what you can do, so you can check this is linear, and but the other tools are not linear, so you can linearize it using the first one. So suppose g1 xy plus say g1 x1 y1 plus grad of g1 x1 y1 transpose. This is x minus x1, which is 1, and y minus 0. So that will become, so this one you can put 1 and 1, so we'll get minus 5. Yeah. Then you have to get the gradient. So the gradient is uh, find out 4x 2y. So that's this is 4 and 2, and this is x minus y minus y, 1. So it's pretty simple. So it's 4x plus 2y, and then you have minus 4 minus 2 and minus 5, so that's minus 11, and this should be less than equals 0. So this could be one Kelly's cutting link. So I think this should be clear to you. Third problem is which of the following is or true for a minimization problem in Sutton-Dykes method. So it's on Sutton-Dykes method. So it depends on the usable direction and the feasible or distant direction. So related to usable direction. So generally what happens, so it's a relation with feasible direction, distant direction. And I think you will get the answer from the lecture slides again. Okay, so this is from lectures. Fourth problem is exterior penalty method obtains a sequence of solutions by minimizing this. Which of the following is not true about the penalty parameter? Okay. Okay, I think you will be able to get it. It's again directly from the slides. So it's sine of penalty parameter Ck and monotonicity. So it's directly from the lecture. Okay, so let me check the fifth problem. Yeah, so the fifth problem is which of the following is not true about the penalty function px of penalty exterior method. Okay, so it's basically px tends to what as x tends to optimal value. I think it's again very simple and directly from the class. So lecture. So that will cover it. Sixth problem is exterior penalty method obtains a sequence of solution xk by minimizing this. Which of the following is true about px? Okay, so yeah, it's again very similar. So I don't find an issue in this question as well. So it's a relationship between exk and exk plus 1. This is again from the lecture. Seventh problem. Exterior penalty method obtains a sequence of solution and which of the following is true. So again, this is this is the relationship between. So you have to think about whether you're solving a more constrained problem or you're allowing for the penalty. So based on that, you can get it. Again, I'm not going into the detail. This is again lecture 8 is exterior penalty method obtains a sequence. Okay, very same kind of problem. Yeah, but this one is QCX is nothing but f of x plus ck of bx. So now it's the relation of this q. I think this one is again directly from the class. Yeah, but do check whether it's the options are correct or not. So there could be multiple correct answers as well. This one is something critical. Okay, so 9 and 10, yeah, I'll discuss it, but let me just check whether the assignment problems are the same that I have talked about, just to be sure. Okay, okay, so I think, yeah, problem 9 and 10 are again some numericals. So it's only three numericals that I present. Yeah, problem 9 is solve the following optimization problem. Okay, so suppose min of fx equals, I'll just change the numbers again, x squared minus 5x, and we are subjected to a constraint. Suppose gx equals x minus 2 is then 0. The penalty function expression is max of 0 comma gx whole square. So you have to solve it. Now what you can do in this problem, so again there can be x star and fx star you have to find out. Okay, so you can write q of ckx, so fx plus ck max of 0 comma gx square, and x square minus 5x plus ck max of 0 comma x minus 2 square. So depending on, so it could be x square minus 5x. So this is if x is less than 2, and we have x squared minus 5x plus ck x minus 2 whole square if x is greater than x 2. These are the two conditions that you have. Now if x is less than equals 2, now this as a minimum at x equals 2.5 just for constraint optimization, right? But that is greater than 2. So now suppose x greater than equals 2, then what you have square minus 5x plus ck x minus 2 whole square. So let's find out q prime of ckx and set it to 0. So that's 2x minus 5 plus ck times 2 times x minus 2, and this will be 0. 2x minus 5 plus 2ckx minus 4ck equals 0. So let's take x as common. 2ck plus 2. This is 4ck plus 5. So x is 4ck plus 5 by 2ck plus 2. Or I can write it down as 4 plus 5 by ck is 2 plus 2 by ck. Okay, now suppose ck tends to infinity, will give you x star equals 2. And just to be sure, let's check the second derivative. That's 2 plus 2ck. So that will be greater than 0. So that means x star equals 2 is the optimal solution. And if x star is x squared minus 5x, which is 2 squared minus 1, so that's minus 6. Yeah, so that's how you solve this problem. Yeah. Freezing language. Okay, so yeah, this is fine. And finally, the 10th one, it's very similar, but let me suppose minimization of say x plus 2y subjected to x square minus 2y minus 4 less than equals to 0. Pxy is again a very similar expression. So you have to find x star and y star. So let me quickly find star star. So the approach could be here is to first write down the expression. That's x plus 2y plus ck max of 0 x squared minus 2y minus 4. So that's equals x plus 2y plus ck times x squared minus 2y minus 4 whole square if x squared minus 2y minus 4 greater than equals 0, or this is equals x plus 2y if square minus 2y minus 4 less than equals So grad of q is, so for the greater than equals to 0 case, let me write it down. So that's x. And for y, so now you have to equate it to 0. So once you remove it, this ck, when ck tends to 0, so that's 4ckx. Okay, so I'm not going into the details. You can set it to 0 and find x and y in terms of ck. So what you can do, uh, yeah, so one equation gives you, the other equation gives you, so assuming, so x squared minus 2y. So if it is not equals to 0 implies x equals minus half. But yeah, so there is nothing, no restrictions on that. So when x equals to minus half, you can also find out y. So that's 1/4. So that's 1/2 ck. So that's okay. So ck tends to infinity will give you minus 15/8. So in this case, x star y star could be minus half minus 15/8. Yeah, but when you have this x squared minus 2y minus 4 equals 0, so that means you don't have this condition at all, the extra condition, and yeah, it will just reduce to your gradient will never be 0, it's 1 up 2. So the otherwise case, so this gives you as 1 and 2, and that's not equals to 0. You need not consider that. So that's all about your week 11 discussions. So I'll stop here, and yeah, I'll wait for 15 more minutes because it's there are still 15 minutes. But if anyone joins and asks questions, but otherwise that's a wrap. And next week also I'll just solve those problems in detail again, the actual ones, and then we'll briefly talk about the week 12 content, but yeah, the rest of the things are, I think, pretty simple. 2 more weeks of class are remaining, and yeah, I think you'll be able to solve the assignment better. Okay, so just another things, I'll just check the discussion forum. So actually, what I noticed is that the queries that you have, I cannot answer those because that's up to the instructors. So yeah, from here I have been mentioned. So this one says, I think the answer of question number 8 is not there in the options. I think it's in assignment 9, and that's absolutely true. It's not there in the options. But yeah, it depends on. So instructors might need to say it and check. This one also, it's week 9, the first question option. Yeah, that's that I noticed. Both option B and D are the same. So even if you choose one of them, it should have been correct. But again, I don't set this assignment problem, so I cannot do anything. Regarding the certification exam, I don't exactly know because yeah, that stands with NPTEL board, I think. So they will only be able to answer it. And finally, this one, yeah, this I could not understand this query. So it says at 1 second of the video. I don't know. So if you have a specific doubt, clearly mention. And also this for assignment question number 8, option A and C are the same. Correct answer not present. It's I don't know in which assignment it is you are talking. He's talking about. But let me check assignment 9 just quickly. Okay, assignment 9, question number 8. A and C are the same. No, it's not assignment 9. So probably the one I solved just now, assignment 10. No, it's not. A and C are not the same. What about 11? Oh, yeah. Yeah, assignment 11. A and C is the same. Yeah, so again, I don't know what's the issue, but what you can do, you can mark C probably here because I think that was the correct one. Anyway, leave it. But I cannot do anything about it because the instructors will only check, or the main tier of the course will check it. Anyway, so that's all about it. And the discussion forums, yeah, um, I'm not replying it to those mails because I don't know exactly. So I'm not probably the concerned authority to reply to those mails. It stands with the instructors of the main tier of the course. But anyway, the issues that you have raised all are valid, except for the video thing that I could not understand at which moment you're talking about. Okay, so yeah, it's around 4:45, some 10 to 15 minutes I'll wait and then I'll leave the call. So yeah, see you next week. Okay, so it's almost 5 p.m. and since no one is here, I'll close the session. Uh, See you next week.